Blue, blue, blue. So now I changed my trousers, so it will be more complicated. Okay. Right, so I think that the plan for today is to first finish this third lecture about collective modes in a two-dimensional Bose gas at the bottom of the shell trap. And then you with a short version of the seminar I gave 2 weeks ago in Newcastle to show you a recent result on fast rotating chain condensates at the bottom of the trap, vortex lattices, tilting on vortex lattices up to the point of the where we have a fast rotating superfluid on the edges of the bubble. So before I detail these collective modes, I will first show you an overview of the collective modes. Remember, we discussed a little bit the spectrum. There were different kinds of low energy collective modes, dipole, quadrupole, etc. So in a two-dimensional gas for a harmonic trap, this is a spectrum we get at low energy. It's a zoom of the full spectrum I showed you yesterday. And this is done for an isotropic trap, but then I will also consider anisotropic traps for particular interesting modes. So the lowest energy mode is labeled. So first, I have to remind you that in a two-dimensional trapped gas, because of rotational invariance, label the modes with two numbers. The n, which is a radial excitation number, and m, which is the azimuthal or angular momentum excitation number, which can be positive or negative. And the spectrum is given by this expression at low energy. So the first mode, the lowest energetic mode, is the dipole mode, for which n is 0 and m is 1. So it corresponds to the center of mass oscillation in the trap. And of course, there are two of them in 2 dimensions, which are degenerate. So if you like, m is plus 1 or m is minus 1, with n equals to 0. Then for n equals to 0, n equals to 1, sorry, so second branch, and m equals to 0, so this is m. There is a monopole mode, which is the same as the breathing mode. So now n is 1 and m is 0, so you're left with this term and this term. And so its frequency is twice the oscillation frequency. And this is a signature of the equation of state frequency of this mode, because with the breathing, you compress or decompress the gas. So you can test the way the chemical potential depends on the density, the frequency of this. Yeah, in a case where you have an equation of state, it's just mu equals to gn. Then if it's not the case, it shifts frequency of this mode. And then the green dot here corresponds to the quadrupole modes, which are present only for a superfluid and not for a classical gas, whereas this one, it's also, you can see it in a thermal gas as just the exchange position of atoms oscillating at the bottom of the trap. And then the radius breathes with twice the oscillation frequency. So this one is specific for superfluid gas. It corresponds to n equals to 0 and m equals to 2. And I represented them like that because in an isotropic trap, m equals plus minus 2 corresponds to rotation with a frequency in one direction or the other one, which is exactly, because those two modes are degenerate, the same thing as saying that you excite the gas by compressing one direction and extending the other one, and it will oscillate like that, or like this. So these are the two independent modes with the same frequency. If we are in a rotating frame, rotating at some frequency, it's not true anymore that this M plus and minus generate, and this can be used to measure the rotation frequency. And finally, when the not isotropic anymore, but there are two different frequencies, omega x and omega y, then you have a scissors mode, which is a link to the quadrupole mode. It's a quadrupole-like mode. It's mode. Because like in the quadrupole, in the center, the velocity field is 0. Everything happens on the edges. It's a velocity field like so this one is like xy, and this one is the other direction. But in any case, it's a quadrupole field for the velocity field. So nothing happens in the center, and only on the edges it flows like that. So it's a surface mode. The scissors is also a surface mode, and it corresponds to a global oscillation of the shape like this. But it's not like you take the atoms and you move them like a block like that. It's all happens at the surface, and the atoms moving at the surface give this overall shape like that. And this also is a signature of superfluidity, so it can be used to probe gas is superfluid or not. It's not present for a thermal gas. Yes? Because if you have you will not have the same spectrum. For Bose-Einstein condensation, you don't need interactions to be present. For superfluidity, you need. And it's a dynamic. So Bose-Einstein condensation means you accumulate a macroscopic fraction in one specific of the density matrix. It's not a signature of that you probe here. It's you probe the dynamics. You're not probing how many atoms are in a given state. So it's different. Without active interaction, you won't have that. You will have it only if there are interaction, and thus it is superfluid. And the other way around, if you have a pure superfluid, not BEC, like in a BKT theory at large scale or whatever you want, we'll have a superfluid test which will work, but Bose-Einstein condensation. So it's a different. This really tests superfluid. Okay, so just to have a look on how it looks like. So this is for an anisotropic trap. This is a wave function of these modes. So this is a BEC at rest, if you like. The dipole modes are illustrated in this way. So blue means less atoms, red means more atoms, and green means the same number. So this drawing, I have to superimpose to this one to see that the dipole oscillation corresponds to putting more atoms on one side and less on the other side. And then this kind of wave function, you oscillate with a cosine such that after half a period, that the other way around. So this represents an oscillation in this vertical direction of the blackboard. This is the other dipole mode. This one is a kind of a quadrupole mode. And this one is a scissors mode. It corresponds to, as I said, the XY average. So it means either I have more atoms in these directions or then more atoms in the other one. So it corresponds to a scissors oscillation. And then there are higher order M modes which come before the monopole mode, which I recall, was this one. So it can be higher in energy than other M modes. for the first branch. So this is the modes are ordered by energy in this calculation. This is a diagonalization. So you first have other m components before with n equals to 0 before getting your n equals 1, m equals to 0 monopole mode. So strictly speaking, it's not the quadrupole and the monopole because in this calculation the trap is anisotropic. So for the monopole you really need to have something isotropic. It's monopole-like in the sense that the different Thomas Fermi radii oscillate in phase, whereas here the Thomas Fermi radii oscillate in opposite phase. So what I will concentrate on are the two dipoles, the quadrupole-like and scissors mode, and the monopole-like mode, which have these kind of frequencies. So in general, if it's not isotropic, these are the frequencies. And if it is isotropic, the quadrupole is square root of 2 omega, and the monopole is 2 omega. So the way we have overall view of these modes is to shake the trap in every possible way, and then observe what it gives. And it moves all around like that. So we lots of pictures, one after the other. So to be clear, this is a destructive imaging. So it means we always do the same excitation procedure, and then we take pictures at different times by repeating the experiment each time, because it's deterministic the way we excite. And when we get a lot of images during a typical time of 100 milliseconds, and then we have to analyze that and wonder which modes are excited in this picture. Yeah. No, because we start from a true BEC in the ground state, very nice, without thermal fraction. So the only thing that changes, but it's not relevant, is the overall phase. But then if you multiply your global wave function by a phase or another, at the end you observe the density, so it's not relevant. But otherwise, we start with a BEC in ground state, very, very cold, and then we apply exactly the same shaking procedure. So there can be some small differences, which are just our experiment-to-experiment fluctuations that we also have anyway. So that in our experiment, we did two things. First, we took always the same picture without changing the conditions, without exciting, and this gives us information about the stability of our experiment. And then we make this shaking experiment where we shake enough such that it overwhelms these the fluctuations which are always there in our experiment. Yes, with very small fluctuations, very, very small. And so what we do to get the modes which are excited is to make a principal component analysis on the pictures, which corresponds to a pixel by pixel correlation of all the 133 images, and then to find the eigen source of the principal component diagonalization of the correlation matrix. And with this, we can identify the independent modes which are excited in our system. So this is the average picture of the 133 experiments. And these are the first components that we extract, except one I have removed. I will comment right after. So the first two we observe are the two dipoles, corresponding to the two main axes of our trap. And then we observe a component which is monopole-like. We nicely see the scissors component. This one is less well discriminate. The more picture we accumulate, and the more the but here we don't have enough pictures. And the one I have removed is a picture which is very similar to this one, and which, if now I the weight of this component with time, it gives me which frequency it oscillates for, but for this one, it decreases exponentially. So this component is a signature of the fact that over our 100 millisecond time, we have a little loss of atoms. That's why it appears as a principal component, but it's not a mode, of course. It's atom losses, which can be so removed. And also, we see silly fringes, which come for our imaging procedure, which can also be removed, can be used as a way to filter your images. So the two dipole modes, the monopole-like mode, which informs us with the equation of state, and the scissors about superfluidity, I will detail that. And as I pointed out already yesterday, to also have the dipole mode present is very important, because it gives us the clock with high precision of what are really our frequencies omega x and omega y. And all the data I will analyze with the scissors, I will always compare to the omega x and omega y of the given experiment. Because it may happen that there are small technical fluctuations which change a little bit this omega x, omega y. And to be able to compare from experiment run of one day to experiment run of another day, I have to clock everything with respect to instantaneous frequency, which I always do. So let me discuss first the monopole mode, which is a signature of the equation of state. If I have an equation of state of the form mu proportional to n to the power gamma, can I get the gamma observing this mode? So for this set of experiments, we use a very isotropic trap, because we want to the monopole, so there is no anisotropy like for the scissors. And so if I have an equation of state which is not just proportional, it gives me a correction to the frequency of the monopole, so it's not 2 omega anymore, but this correction is proportional to the way the chemical potential depends on the density. So it will give me with my gamma, it will give me a gamma minus 1 a term for the epsilon. So this also has been used in Rodecrem's experiment with fermions to probe the equation of state. So let me consider a few possible equation of states. So if I have a 2D weakly interacting gas, a very nice and usual 2D gas, not too strongly confined transversally to avoid problems, then I have the regular equation of state mu equals to Gn, and I expect a frequency at 2 omega. Now, then remember what I told you about going too far by compressing the atoms. Then, in this case, you have another length scale which appears in the problem, this A2D. And because of that, you get a change of state, which is proportional to n, and you expect a positive shift, a very small positive shift, which to first order is equal to our G tilde dimensionless coupling constant divided by 16 pi. So 16 pi is large, okay? So remember, in typical experiment, we can go to G tilde is 0.12, something. It's very hard to go to large values. So if you divide that by 16 pi, you see that the correction to your monopole frequency is rather small. So here it is. I show you that, and then you ask, okay? Because here is a general quantum anomaly, so I will be fast because I'm not the theoretician with all that calculation. This is Maxime Ranchani who did that. But the idea is the following, that remember in 2 dimensions there is a scaling invariance where k squared scales like the interaction. So you have 3 operators which form a closed algebra for the classical case. When you have the generator of scaling transformation, which is this operator, which when commuted with the trapping energy goes back to trapping energy. Commuted with kinetic energy or interactions with scale the same goes back to kinetic energy and interaction. So this is what it means that there is a scaling symmetry. And if you commute trapping energy and kinetic energy interactions, you go back to the scaling. So this is closed. But now, if you really consider a strong 2D regime, and you want to quantize these Poisson crochet commutators, there is a small leakage, this commutator, into other observables of scaling transformation, stays, well, when commuted with the kinetic energy or interaction, stays in, with the Hamiltonian, stays into the same ensemble of 3 observables. So because of that, this is the intrinsic reason an A to D, and you have a shift, an equation of state, and then a shift in the monopole frequency. Now, I can take your question. I don't know if you. Yeah, okay. What I can tell you is, if you put A to D going to 0, then you're back to the usual case where everything is nice and scales. Because it's not true when you quantize purely in 2D that you will 2D being 0. It's not 0. So you left with a parameter which enters into the equation of state. It's a small correction, but it is still there. So I think, okay, let me continue probably. So this motivated us, in fact, to try to see this anomaly in an experiment. And I also want to point another equation of state which is relevant if you think you have something which is a gas, but very, very flat, an oblate gas, but still 3D in the sense that you have a Thomas Fermi distribution in all 3 dimensions. So I said you go to 2D by compressing such that you go in the ground state of the harmonic oscillator. But you can also consider the case of an oblate gas, where it's completely Thomas Fermi in all 3 directions, except that you let the ratio transverse frequency over plane frequency go to infinity. So it is very anisotropic. Omega z divided by omega perp goes to infinity, but you always conserve the Thomas Fermi just in all 3 dimensions. So if you do so, the monopole mode for the transverse directions is square root of 10⁻³ omega, because the equivalent equation of state when looked into the 2D plane, so it means you integrate out the 3rd direction, scales like n to the power 2/3. So again, this works with this formula. Okay, so what we did is to try to probe the equation of state by looking at the frequency of the monopole mode. You see that we should be between 2 omega and square root of 10⁻³ omega, depending on how 2D we are. Except if we also can observe the quantum anomaly, where it should be even larger than 2 omega. So we probe the monopole frequency as a function of the chemical potential divided by h bar omega z, is a way of measuring how we are. Because if the gas is very 2D, then the chemical potential must be much, much less than the transverse energy. Remember, 2D means transverse energy larger than any other energy of the system. So the way we probe the monopole mode is to abruptly change the frequency of the trap, which sets the gas out of equilibrium. Then it is, and we record the oscillations in the radius as a function of time for long times. So typically, we do not observe any damping of this oscillation, which is expected for the Pitevsky-Roche mode. And the frequencies are always very close to 2 omega. So here are our data points of the measured frequency as a function of this parameter mu over 2h bar omega z. And the blue line here is the expected anomaly. So what I can say first is that the anomaly shift expected for our system is so small that it is below our typical error bars, so we cannot really observe that. However, what we see is that there is a shift towards the negative, towards values lower than 2 omega in our trap when we increase the atom number or we increase mu. And for example, for this kind of data, we observe a modified equation of state where instead of being proportional to n, it's proportional to n to the power of 6 or something. So this is confirmed by performing a 3-dimensional Gross-Pitevsky simulation, where we take into account the fact that it's not the gas, but there is a third direction. So even if they are very, very close to being in the ground state, because mu is very small as compared to 2h bar omega z, okay? But still, the interactions, in fact, are able to populate a little bit the transverse direction sufficiently to modify the equation of state and modify the observed monopole frequency. So it fits really nicely with a prediction of Gross-Pitevsky simulation. And after that, performed also a perturbative theory from the value 2 when we take into account the inflation of a transverse ground state due to interaction. So we renormalize all the ground states by some effect of the interactions. And we were able to also predict the slope observed at small values of mu because it's a perturbative theory, so it's valid for mu very omega z. And this, let me point out that it is a PhD work of Carina Merlotti, who is Brazilian and studied first at University of São Paulo. Okay, and so we did not observe the anomaly, which was small, but let me point that this has been observed very recently with fermions simultaneously in the group of Zelim-Yochim Veil, where they make use of Feshbach resonances, because what was limiting us is that we were varying the confinement by, well, the value of G tilde by confining more or less, which is not enough. It's scaled just with the root of the trapping frequency, whereas they have a Feshbach resonance, so it can really go to larger values of G tilde and a shift which is much larger than our very, very small shift. You see here it was like 4% shift, and here more or less the same. If we had a 4% shift, you would see it. We had 0.0 or something %, so it was too small. Okay, but for boson it has not been observed yet, only for fermions. So this brings me to the second mode I wanted to present, the scissors mode, and the way we use it to probe superfluidity. So I remind that the scissors oscillation corresponds to the oscillation of the xy momentum, which for small values of the angle is proportional to the angle, but the true parameter which oscillates with the real mode is this one. So we probe it anisotropic harmonic trap 0.3, and if the gas is superfluid, we expect an oscillation at square root of omega x squared plus omega y squared. And if the gas is thermal, we expect no specific mode, just a bit node between the component oscillation of the trap. Because you remember you measure xy, so if x oscillate like cosine omega x and y oscillate like cosine omega y, then as you compute the average of the product, you will have the bit node between omega x and omega y. So the question is, how does the superfluid fraction, or how does the superfluid react when you cross a critical temperature? And so we were looking at this mode as a signature of superfluidity across the BKT transition. And one motivation was the fact that in 3 dimensions, this has been done in the group of Chris Foot, and they observed that at low temperature, they have the scissors oscillation. At high temperature, they have the 2 omega plus minus y frequencies. And there was a middle region where they see the 3 of them, and they see, when increasing the temperature, a negative shift of the scissors frequency due to the presence of the thermal gas. Whereas there were numerical simulations in 2D, which seemed to indicate that first, the transition occurred on a very smaller scale, and it was more going between the scissors oscillation to the omega plus oscillation, and not really to negative values, so we wanted to study that. So the way we do it is we prepare an anisotropic trap. Thanks to RF bubble, we can control everything with the polarization, amplitude, etc. We instantaneously almost change the main direction of the trap. The gas is out of equilibrium. It oscillates, and we record the oscillation of the average value of xy as a function of time. So we see typically 2 kinds of behavior. Either the temperature is small, and we see a single frequency, which is slightly damped, or we are above the critical temperature, and we observe, in fact, 2 frequencies. You have a fast frequency, which is larger than the scissors frequency, you see, plus a slow frequency corresponding to omega minus and strong damping. So here is the 2 kind of frequencies we observe. So in fact, in the 2 branches corresponding to this upper branch and the lower branch where it stops. So now it's plotted as a function of the reduced chemical potential. So it means very low reduced chemical potential thermal gas, and large reduced chemical potential condensed gas. When the chemical potential is very low, indeed, we observe the 2 omega minus and omega plus frequency, which correspond to the thermal gas. When alpha is very large, we observe just the scissors frequency, and here, when it is 0, it means that there is just 1 frequency, no other frequency, in fact. And then we observe well, many points where we see some shift, etc. So we would say, by seeing the data points, that, okay, here it is thermal, controlled somewhere here. Now if we compute what we expect for the BKT transition, the critical value of the reduced chemical potential is here. So we see a lot of points where there is a shift, but still we see mainly the thermal oscillation frequencies and not the condensed one. So what's happening? This is obtained by taking the value of xy over the whole gas. So now, instead of doing that for 3 characteristic points, make an analysis which is more local. So instead of making this average value of xy over the whole cloud, we make this average value over a thin annulus. And the reason why we do that is that along a thin annulus like that, we have a density which is more or less constant. So we expect to, or not, a superfluid, but that at least the criterion will be the same for this annulus. And so we redo the average value of xy over only part of the gas over the thin annulus. So with respect to these data, as we make average over a sub-fraction of our sample, there will be more noise. but still we will learn more. And we look at 3 cases: a case where alpha is much larger than omega alpha c, alpha is larger but not so much with respect to alpha c, and alpha below alpha c, corresponding to these 3 situations here. Okay, so first the case where it is strongly degenerate. And we look at the observed frequency radius per radius on this circle. So with all the frequencies we get corresponds to the scissors frequency. It's everywhere the scissors frequency. Here it is 0, it means there is no other frequency in the system, just one, just the scissors. And you see also that at small values of the radii, we have a hard time determining anything. And this is normal. As I recall that the scissors oscillation is a surface mode. So if you look in the center, essentially nothing happens. The gas doesn't move. So of course we are not able to determine the frequency there. But if we go a bit away, we see it very clearly, and it's just the scissors frequency. Now, if we look at the situation where we have a temperature larger than the critical temperature, or a density smaller than the critical density, so we expect a thermal gas everywhere. On the edges, indeed, we see very nicely the 2 frequencies omega plus and omega minus, which are almost as expected, a little bit below. And when we enter the center of the gas, we see a small shift, which I can comment on later if you want. But this essentially works, and we never see the scissors frequency. It's always far from it. Okay. Now, if I take the funny points, which I expect are degenerate, and well, still I see a frequency close to the thermal 2 frequencies, here is what I find. So at the edges of the gas, I find frequencies very close to the thermal frequencies omega plus and minus. But inside the gas, much to the center, I recover the scissors frequency by local analysis. So what was happening before is that when I take the average xy, I give more importance to large values of xy. And so the contribution to the oscillation was larger for the thermal gas, which is away, and less important for the central part. So it was masked. The fact that in the center the superfluid is masked by the oscillation of the thermal. But if I look radius per radius, I recover the fact that I have a superfluid cloud at the very center, surrounded by a thermal cloud, and you can see that it is rather sharp, the position where it goes from superfluid to thermal. And now if I compare with the local density approximation where in the gas I expect to have the BKT transition, I find that it corresponds more or less with the transition I observe, with some small shift, which can also be due to what I said. I have a finite system, and I have a little bit of superfluid going above this, beyond this region. Okay, it's not the BKT temperature. It's a BKT. You can translate radius into chemical potential. My alpha is the reduced chemical potential. Because T is constant in my sample. I have one sample with a fixed T, and then alpha is the parameter, the ratio of chemical potential divided by temperature, and it is a local alpha. That's what I explained yesterday, in fact, with LDA. I'm sorry, so I can go back. But I said, okay, what is relevant is my local value of alpha, where I remove the potential energy, because I know that the density is smaller because of the trap on the edges. So now my alpha in the center is a peak alpha, but on the edges it is smaller. So scanning the radius is like scanning alpha. So somewhere I expect my critical alpha to be reached. So either I have a cloud which is very hot, and then even in the center I am not yet at critical alpha, or I have a gas which is very cold, and then my critical alpha is towards almost the edges, or I am in between the two regimes and I have a critical alpha somewhere at a given radius, and this is what is plotted there. Yes. Yes, there is a prediction given by classical field theory, so I have not given it, I'm sorry, for the critical temperature, which is a log of G tilde over 350 and 80. So you can, from the knowledge of G tilde and classical field theory, there is a paper by Svistunov and Prokofiev. With this, you can very well estimate the critical temperature. And then you can take into account the transverse direction, and this is done by Holtzmann and Kraut. And you take all the elements of the theory into account, you can make a good estimate of where you expect BKT to occur. So this gives us hints on where the gas, the superfluid to thermal transition occurs. And so one dream would be, could we see something like a jump? But again, it's a finite system. So calling it jump is a bit too much. But something we could wonder if can we extract, for example, the superfluid fraction from this kind of frequency measurement. So this, I don't know, it's still an open question. That I said also. So yes, it's a bit cheap. So first, it can be an issue of estimating the local density. We have two ways to estimate it, and either it's a blue line or it is a magenta line, which is a bit closer. And second, even, so this was at the beginning. No, maybe, no, I don't have it here, sorry. So, and even like that, we do not expect that there is no superfluid, that there is no superfluid at all here. Because we asked Markus Holtzmann to make this Monte Carlo calculation in a finite system for our case. And what he sees right at the critical value when you perform, you already have some value for the superfluid fraction, and a little bit also in the normal region because of finite height and proximity. So this also is very hard to determine quantitatively. And this is also an illustration of the damping of these curves. And in fact, the points that you get of the damping frequency as a function of the scissors oscillation nicely fit on a hydrodynamic curve. So those points here correspond to the pure degenerate case, superfluid case. And here it's more the thermal gas with the two oscillation frequencies. But we have a damping which also corresponds to what we expect. And okay, this here is the damping rescale to the frequency when we split the cloud into two regions where the boundary is determined by the alpha C given by local density approximation, and we now compute the XY value, not radius per radius, on all this region or all this region, and then we can have a little bit signal to noise ratio. And we see that at low damping and in the condensate, it is very similar to what we expect for Landau damping, but then at higher temperature, there are interactions with gas, and we are away from that. Okay. So this I think I will just skip and summarize that we can use these collective modes to get information from our gas, get information concerning the equation of state, especially if we use a monopole mode, information about the superfluid character of the gas, even a local information on the superfluid properties of the gas. And then knowing if we can measure the superfluid, that is it's still an open question. And so these were 2 slides I added to say that the things we have not spoken of. So this was shown already by Natalia the first day. Once we have this bubble, we can also wonder what kind of modes we have with everything with a coherent gas. And this has been studied recently, where essentially you can have, again, some kind of monopole mode here, some kind of dipole mode here, etc. So the monopole mode, or the easiest mode, corresponds to the transverse trapping frequency, where essentially it oscillates with this frequency, and then you have. So this would mean that shell does this. So this is at the trough frequency because everybody goes in, out at the same frequency. And then you also have a monopole-like excitation where the shell itself breathes. And then, as it is a quasi-1D system, you find a square root of 3 in this situation. But this nobody has tested experimentally. Okay. And second, this will be the bridge to my seminar-like talk. When we perform a fast rotation inside the bubble, we can reach a situation where we have the atoms creating a flux, a flow, above the bottom of the bubble just because of angular momentum. Okay, and I wanted to acknowledge the people who contributed to this work. So Carina Merlotti for the monopole experiments, Camilla De Rossi for the scissors experiments, who were the 2 PhD students, and then for the experiments in the bubble trap and the rotating gas, it's a topic of the PhD of Mathieu de Guerre and Yan Guo. And the permanent people working in the lab on these experiments are Laurent Chambon, Thomas Badre, Romain Dubessy. Avinash Kumar was a postdoc with us who worked on a slightly different topic, but who participated also in the analysis of the fast rotating experiments. And we have nice collaborations with a local theoretician, Paolo Pedri, and also people outside the lab, Maxime Alchani for the monopole experiment, Barry Gawawe for all the RF, the theory in RF traps, and recently Van der Leyen also, with whom we would like to see what's happening inside the bubble when we shake strongly and go into more excited regimes. So thanks for attention and now we continue. So don't be too. I hope you won't be shocked if I use the Newcastle seminar, okay? Because I have not prepared something specific, and I will probably go